So today we will look at a priori error estimates for ℎ-P and ℎ-P-FEM. As I was telling you, this is actually one of my favorite lectures, if not the favorite lecture that I teach for this ME 46050. And the reason for that is that we're going to learn what the theory tells us about how approximations are supposed to converge. And in this lecture and the next lecture, we are going to learn also how to check our implementations, right? Because as I discussed last Friday, if you have to take one thing from me, what was it? Who can remember? One thing. How do we build the code?
Function by function.
We make small pieces of code. These are our building blocks, right? We test them. Once they work, we do something, we make a test, and then we move on. And this is the way we can create very, very complex pieces of software by always working in small pieces of code, right? So whenever we have a problem, we have to try to simplify it, right? And if we have a bug and we need to figure out where the bug is, right? We try to make a test, the simplest tests that shows the bug. Then with the bug, we finally get it working, and then we move on. This is the way we can build software. So today we're going to look at a priori error estimates. But of course, before we do that, we need to talk a little bit about the mechanisms behind ℎ and ℎ-FEM. You already know how they work, the rationale behind both methods. And we're going to see that there are different types of problems. So there are smooth problems, and there are non-smooth problems. And we're going to see a couple of examples of them. And then we get into the problem classification. And then we're going to classify problems into three categories. Finally, we get into the theory, how ℎ-FEM and ℎ-FEM can actually converge. What is the error of, how the error is reduced as we increase the approximation accuracy. And then at the end, we're going to look at the ℎ-P version of FEM. Okay, well, we already know the mechanisms behind both ℎ-FEM and ℎ-FEM. So for ℎ-FEM, normally we are working with linear or at most quadratic finite elements, Lagrangian elements. This is what you normally find in your favorite software package, right? And well, the idea is that we improve the approximation by reducing the mesh size. It's very straightforward. We expect that as our elements become smaller and smaller, right, we increase the approximation and we reduce the error. And for the most part, ℎ-FEM is very successful because you have to have small meshes anyways, right? So there are, if you have to model some mechanical component where you have some sort of stress singularity, the geometry itself is so complicated that in any case you need to generate a mesh size that is small enough to be able to capture the geometry accurately. And so, yeah, ℎ-FEM actually works pretty well. So in this case for ℎ-FEM, where you reduce the error by just making the mesh finer and finer, then obviously the error is going to be controlled as you see here as with the largest element. So that is the one that is going to control the error. Of course, there is a subtlety there because sometimes the error may be very, very high in regions where you have a high stress concentration, right? And you still have a smaller mesh size, right, than in other parts of the domain where your solution is smoother, but you have a larger element size. But in any case, if you assume that your problem is smooth, your error is always going to be controlled by the largest element size. Okay, so that is the mechanism behind ℎ-FEM. ℎ-FEM works differently, as we discussed already multiple times. Well, you normally keep your mesh fixed, but you increase the approximation order, right? The polynomial order of your interpolant, right? And well, we said also that when we are dealing with isoparametric formulations, right, the geometry and the field are approximated with the same polynomial order. But obviously, if you now have your mesh fixed and you increase the polynomial interpolation order, that doesn't necessarily has to be the case, right? We can actually keep our geometry to a lower order, in which case this formulation was called subparametric, right? So remember, we always look at the geometry to see whether it is subparametric or superparametric, right? Or isoparametric. So in the case of 𝑝-FEM, again, assuming that you have a smooth problem, the error is going to be controlled by the element with the lowest polynomial interpolation order. And it is possible to mix different types of P elements, right? You can have linear elements in some parts of your domain where you don't actually need high accuracy because the solution is smooth, and then you can increase the polynomial order as you move to more complicated regions, okay? Right, let's take a look at two types of problems so that we can understand how the theory works. So imagine you have this bar. Again, you have this load per unit length, as you see here. You also have the displacement field plotted, which is actually very, very smooth. So it's a trigonometric function. And so what theory predicts is that if you take ℎ-FEM, right, you get some sort of convergence that looks like this. Right, so the convergence rate, which is the slope of that line in a log-log plot, is going to be more or less constant, right? And now, if you have a 𝑝-FEM implementation for that very, very smooth problem, you should have something that looks like this, right? So now the convergence rate is actually changing if you increase the polynomial interpolation order, right? So this is the so-called exponential convergence rate, right? And we will see what we can do, because obviously there is no proper slope in that curve, right? Which slope you take. It makes no sense. But what we will see later is that actually if you take the log of this plot, then you get a straight line. And then theory predicts that that slope has some value, okay? But this is for a smooth problem. Now, if we take a look at this problem, right? The exact solution has some sort of singularity, right? So as we approach x equals 0, then for that particular shape of the load per unit length, as you approach x equals 0, this goes to -infinity, right? And this is a so-called non-smooth problem. And for these type of problems, what theory predicts is that you're going to have algebraic convergence rates also for 𝑝-FEM. So that would be the difference, right? Now, it may converge faster, but the convergence rate is still going to be algebraic. So we don't recover an exponential convergence rate unless we do something special, and we are going to talk about that too. All right? So then you can think, well, let's try to think about a classification for all the problems based on the regularity of the solution. And by that I mean, if we can write the exact equation, right, that exact equation, that exact displacement field is going to live in some Hilbert space, right? And so if the function is very, very, very smooth, that Hilbert space is going to be of order very high. If it is not smooth and there is some sort of singularity on the domain, that is going to lower considerably the space, the Hilbert space, right? The order of my Hilbert space. And so a first category A, this is comprised of functions that are very nice, right? Very smooth. And so in this case, we can say that the field U is analytic function, so it can be expanded in Taylor series. That basically means that, yeah, our field is very smooth. And so you would expect the 𝑝-FEM to give you exponential convergence, and ℎ-FEM, again, as we discussed, for smooth problems, are going to give you algebraic convergence. But at least problems in category A are those that are nice. Category B, less nice, right? Now, U is analytic, but there are a set of points of zero measure, and we're going to talk about that, where things get bad, right? You can think of a singularity in the case that I showed you in the previous slide, right? As we approach x equals 0, the solution went to -infinity, and so, but that is at a single point, right? And so you could say that a point in 1D is a set of zero measure, right? Remember, we discussed also in the nonlinear mechanics course, we discussed this notion of measure, right? When we think about measure, we're thinking about length in 1D or area in 2D and volume in 3D, right? So if I think of a set of zero measure in 1D, well, obviously a line in 1D has a finite measure, right? So a set of zero measure in 1D is a point. Now, if I go to 2 dimensions, a set of zero measure would be what?
Still a point.
A point is a set of zero measure in 2D. What else? Huh? An edge or a curve, that is also a set of zero measure, right? Now, if I go to 3D, I have points, I have curves, and I have surfaces, right? A surface in 3 dimensions is a set of zero measure. So we're going to categorize those problems where something interesting is happening in set of zero measure as those in category B. So you could argue that these are problems that are harder to solve by FEM. And then finally, well, category C, these are the nasty problems, right? The nasty problems for which U is neither in category A nor B. And so you could think now that things get tough, even in set of non-zero measure, right? So sets of finite measure, things are going wrong. There are problems that are interesting. For instance, I can immediately think of a problem where if you try to model the so-called Flamand problem, which is basically a semi-infinite space, and then you just place a load, a concentrated load on the top. As you refine your mesh, your strain energy keeps increasing, and so at some point you have to do something to get some sort of finite strain energy, right? You have to basically remove the element because the displacement at the application of the load gets basically going to infinity, right? That's a nasty problem. So I can think of that type of problem that is going to exhibit or is going to create difficulties for the finite element method. Okay, but now that we have these 3 types of categories, then let's talk about a priori error estimates, because this is basically what theory is going to tell us, how the FEM, ℎ-FEM, and ℎ-FEM are going to behave for each one of these problems. Okay? Well, if you take a look at ℎ-FEM, the theory tells us that the error is going to be bounded by this expression, right? So if you remember, U minus UH is what we call the error. So U here is the exact solution, and UH is the approximate solution, right? So if I take this guy here and I put it into the denominator, so I have some relative error, right? So it's the relative error in the energy norm. So remember, we're looking at the energy space because we're actually interested in the bilinear form. Remember that we had these expressions that were linking the way we are measuring quantities in functional spaces, right, to the bilinear form. And so we are always interested in looking at the error in the energy norm. So we're looking at error in the derivatives, right? And so what this is saying here is that in ℎ-FEM, the error is going to be bounded. So bounded, this is an upper bound, of course, right? By C1, which is a constant, independent of the mesh size, multiplied by h to the power of beta h. So h, as we all know, is the mesh size, right? And beta h is going to be our convergence rate. This is what theory tells us. So, well, if you take the log of that expression, right, and then let's take the limit, because asymptotically this bound is very sharp, right? So we get rid of that inequality, right? And we define, again, that epsilon. There's a typo here. This should go away. So you define the relative error in the energy norm like that. You take the log at both sides. And so if you look at this expression, so if you plot that error as a function of the size h, what you see is that as I get into smaller and smaller h, of course the error is going to go down. And then we get this equation of a line. And you all know that already. Some of you have already obtained some convergence rates in the project, right? And so you see that beta h, which is what we call the convergence rate, is pretty much the slope of this line. okay? And again, that line is expressed like this, right? So in ordinates, we have this guy, right? In abscissas, we have this guy here. And then, of course, this guy is going to be some sort of constant value that is going to move that line. But the slope is not going to change for a given version of ℎ-FEM, right? Linear, quadratic, of course, it's going to have different slopes. All right. Now, we do the same, but we take a look at the number of degrees of freedom of a problem. Of course, and we do this because when we move to ℎ-FEM, talking about the mesh size makes no sense anymore, right? The mesh size is going to be fixed. And so we also normally look at the number of degrees of freedom and how the error reduces when you are increasing the number of degrees of freedom, right? So for ℎ-FEM, what error tells us again, keep in mind, this is the way it's bounded by this expression. This is the same expression we had in the previous slide. But for uniform meshes, you can actually relate the mesh size with the number of degrees of freedom with this expression, where D is actually here the dimensionality of our problem, right? So notice that we get basically something that looks very similar, right? Obviously now we have negative slope, because now as I increase the number of degrees of freedom in that direction, obviously I'm going to decrease the error. And so now we have negative slope. But something interesting is that now the dimensionality shows up there. So in 1D, and this is very important, right? In 1D, we're going to have the same, let's say beta H is going to be the same regardless of whether you look at it versus H or versus the number of degrees of freedom, right? But when you move to 2D and you have a two-dimensional problem for which you need to get convergence rates, now we should get half of that, right? Because now we have dimension 2. This is important also for the project. The second problem, now you are moving to 2 dimensions, and in the second problem, when you compute your convergence rates, then this is going to play a role because now you are in 2D. Okay, this is for ℎ-FEM. Let's take a look at ℎ-FEM. Yeah?
Is D going to be the same as the number of degrees of freedom or not?
D is the dimensionality of your problem, right? So ND here is what I call the number of degrees of freedom, and ND, of course, for, let's say, ℎ-FEM, and I say ℎ-FEM because ℎ-FEM can also show algebraic rates of convergence, right? Obviously, since H makes no sense anymore, but you are going to increase the number of degrees of freedom as you increase the polynomial order. Yeah?
Does the degrees of freedom amount include the boundary nodes where the boundary conditions are applied?
Well, normally I account for those degrees of freedom, but it doesn't really matter, right? Like everything that is boundary is comprised of nodes along a lower dimensional manifold. So asymptotically, remember that all these estimates are sharp when you increase asymptotically the number of degrees of freedom. Yeah, asymptotically those don't matter. So it's essentially the same. Yeah?
If you have like only 2 elements, then it does kind of then it is visible if you count.
Yeah, but again, these convergence rates are sharp asymptotically as the number of degrees of freedom goes very, very high. So for that case, we never really take the convergence rate with coarse meshes. They have to be always defined on fine meshes, and on fine meshes, the number of degrees of freedom that are tied to the boundary is just a very small fraction, because again, it's a lower dimensional manifold, right? Like a curve in 2D, for instance, right? If you account for the number of degrees of freedom, as you reduce the mesh size, for instance, that is going to be just an increasingly smaller fraction of the total number of degrees of freedom.
Convergence rate doesn't matter, but for the
Yeah.
plot, would you like subtract them or?
No, I always consider them. Yeah? Okay, let's take a look at ℎ-FEM. Let's see how ℎ-FEM behaves. Well, as it turns out, theory tells us that the error in ℎ-FEM is bounded by this expression, right? So now we have another upper bound, where here you have a constant c, and you have e to the power of gamma nd to the theta, right? And theta is a constant. Gamma is also a constant, right? So again, if I take this guy here, then I have the relative error in energy, in the energy norm. And then when I take the log of that expression, then I get something that changes the rate as we increase the number of degrees of freedom. And keep in mind that I don't plot I don't plot the error in energy norm as a function of h, because as we discussed, h makes no sense anymore. H is going to be fixed. And so this expression looks like that. And notice that this is something that I can work with, right? So if I can actually take the log again, and I have to, of course, change the sign of the inequality, because otherwise I have problems in the way I compute the log of something that I should not be computing log on. Then I get this line. And what you see here is that now I have the equation of a line with some slope theta, right? That slope shows up there because, of course, here it is basically the exponent of the number of degrees of freedom. And of course, we're going to classify, and we're going to see the behavior of ℎ-FEM for different types of problems, and then you will see that theory predicts that this theta has to have some values. Okay, but this is the way it works for ℎ-FEM. Now, as I already discussed as well, for some problems, ℎ-FEM is not going to exhibit exponential convergence, but is going to be limited by algebraic convergence. And for those cases, now the expression is shown here, so it's going to be bounded by this expression. So now you notice that p to the power of beta p is now the convergence rate for ℎ-FEM, right? C2 is now a constant, but this p denotes the interpolation order, right? So again, when we take a look at that expression and we apply the log, we get this the equation of a line. Again, for sharp bound, then this inequality becomes an equality because we're always looking at asymptotic convergence rate. And then you notice that the curve has a negative slope, and that is, of course, obviously because as I increase in the polynomial interpolation order, the error has to be reduced. And these are all schematics, but as you will see in the project, you're going to obtain numerically the results, and they have to look pretty close to this because, again, this is what theory tells us. All right? All right. So let's take a look at let's make a summary. So here, K is the so-called regularity of the solution, the exact solution as we discussed. So for very, very, very smooth problems, then K is going to be very large, right? And for non-smooth problems, K may be much lower, and it may end up deciding on the convergence rate. So for problems in category A, which you remember were the very nice, very smooth problems, the convergence rate is equal to P, all right? And this is, again, when I'm plotting as a function of H. Remember that when we are plotting as a function of the number of degrees of freedom, then we're going to have an issue there, right? Because then the dimensionality is going to enter the picture, and so we're going to have to divide by 2 in the case we're dealing with a 2-dimensional problem, or we have to divide by 3 in the case we're dealing with a 3-dimensional problem. But for the case of ℎ-FEM, you see that beta h is equal to P. So for your problem, the one that you are solving in your project, right, the first exercise, if you are dealing with a linear interpolation order, your beta h should be 1. And if you're dealing with a quadratic Lagrangian element interpolation, it should be 2. And it should be very close to it. If it is not, we have a bug. Again, remember that here we are assuming problems in category A. Those are smooth problems. Yeah? Now, in category B, things are trickier, right? Because, well, you can say I am going to create some sort of optimal mesh, so I'm not going to keep the uniform mesh. So the element size is going to change, and I can think of, okay, I'm going to change the element size as I approach some complicated region with with some singularity. And if I do that, well, I can recover the convergence P. But for the most part, close to that point, if I just use a uniform mesh, right, then the convergence rate is going to be bound by that expression, which is a minimum between p and k minus 1. So if k happens to be low, right, then is going to bound the error. The singularity is going to bound the error. And indeed, for instance, I can think of cases where for instance, for a problem in a crack in 2D, where we have a singularity at the crack tip, for instance, right? If you plot the convergence rate, right? So if you take the error in the energy norm as a function of the total number of degrees of freedom, instead of getting 0.5, remember that now that dimensionality enters the picture, right? So then it should not be 1 because it's 1 divided by 2. That is optimal convergence. But if you just use a uniform mesh, you don't get 0.5. You get half of that, right? And that is because we have a crack. And the crack is entering here, right? And this guy, K, the regularity of the solution, is going to dominate the convergence rate. And then, well, for problems in category C, what the theory tells us is that, well, beta H is just going to be positive. So you are still going to have convergence. It just happens that for those more nasty problems, right, that you're going to have very hard time converging to the exact solution. So the error is going to go down very, very slowly. Yeah?
How can you calculate K?
Sorry?
How can we calculate K?
Well, K is normally, so there are some problems for which you can obtain an exact solution, right? So for instance, you take the whole research on linear elastic fracture mechanics, dealing with cracks. You can obtain exact solutions using some sort of advanced approaches, right? You can have area stress functions, and so people in the past, lots of people were working in trying to derive analytical solutions for problems that are actually not practical, because like they were analyzing an infinite plate. Well, there is no infinite plate, right? So you have to have a finite plate at some point. But there are still ways to come up with exact solutions for those problems. And well, the exact solution shows you what is the regularity. So where that solution lives in terms of the Hilbert space, what is the regularity or the smoothness of the solution. I could also think of a nice way to compute that using FEM, right? So you can, let's say you have a problem, and then you don't know where the solution lives because you don't have an exact solution. Well, just run it with FEM, and then you look at this guy here, right? Then you can pretty much pinpoint numerically what the regularity of the solution is, because theory tells us that would be, yeah? Okay, so this is for ℎ-FEM. Now let's take a look at ℚ-FEM. So for ℚ-FEM, again, for smooth problems, remember that we recover exponential convergence rates, right? So if we take that initial equation of the bound and then we apply the log twice, obviously we have to do something so that we can actually apply the log twice, then we can recover that coefficient, that constant theta, that was basically, if you recall, the slope of that second time that you took the natural logarithm. And so what theory tells us is that that constant is basically greater than 1 over d, where d is the dimensionality. And in the book, I actually do solve an example with using ℚ-FEM where I can indeed recover that is the case. I'm not asking you to recover that constant in this project, although you can really recover it, right? There is nothing to prevent you from doing that, but I'm not asking you to do that or report it, although that's actually a nice addition for the next time I do this. Anyways, now for category B, then ℚ-FEM is going to converge like that. It's just going to be an algebraic convergence rate as we discussed, right? Again, category B were those problems where the solution was analytic, except for sets of zero measure where the solution can go wild, right? And then finally, similarly to the ℎ-FEM, ℚ-FEM also exhibits algebraic convergence rate for the more nasty problems in category C. Let's talk about ℎ-𝑝-FEM. Yeah, you have a question?
Yeah, my question is, the A equals 100 version of the project, can it be considered a category B problem because of the high...
That is a very nice question. So the question is, for the project exercise 1, when we move to A equals 100, which basically makes the problem very smooth, can that be considered in category B? And that is actually a question that I would like to reflect on. So I'm not going to give you the answer, but you have to try to understand whether it is in category A or B, depending on the results that you obtain. Yeah? So again, we are going to see, based on theory, whether we are here, let's say for ℎ-FEM, or whether we are here. If you just happens to find out that the convergence is not exponential, right, for that harder problem with a stronger gradient, then you would place that here. Otherwise, you would place it here. But this is one of the things that I would like you to think about. And of course, if you recall, I give you one page so that you can draw your conclusions about the first exercise. Well, also about the second exercise, but this is where you have to try to go beyond what you have done, right? We talked also about conclusions, remember? Conclusions try to go beyond what someone can comprehend by just reading your report, right? You have to go beyond. All right. So let's talk about ℎ-FEM. So if we have ℎ-FEM, right, and we have ℎ-FEM, well, obviously someone thought about combining these two to take the best of both, right, and make a more powerful method. That is called the ℎ-P version of FEM. And so what theory tells us is that if you do that, and I'll talk a little bit how you are going to do that, well, it turns out that you also recover exponential rates for the smooth problems, but you also recover now for problems in category B, which were the nasty problems, you also recover exponential rates. But of course, you have to do something special on the way you define your polynomial interpolation order in your elements as you are approaching the singularity, and also you have to do something with the mesh, right? Well, some work has been done on this, and then what basically the way you come up with a very nice way to structure your mesh to recover that exponential convergence rate for problems in category B is shown here. So essentially what you do is far away from the singularity. So let's assume that you have a singularity at x equal to 0 as in the previous example. So far away from the singularity, where you know that your solution is actually smooth, right? Then your element size can be very large, right? And your polynomial order can be very high. But as you are approaching the singularity, what you do is you reduce the mesh size. You make your elements smaller and smaller, which makes sense because, yeah, you need to capture that singularity better, so you need to make your elements smaller. And your polynomial interpolation order gets also smaller. And you say, well, why would you do that, right? Why would you make your polynomial interpolation order? Well, in a way, you think about it this way. As I am making my elements smaller and smaller, I want less complicated behavior inside the element. So close to the singularity, I want my elements to behave linear, and far away, I want to behave in a more smooth way, higher interpolation order, because I know that the field is smooth, right? Well, it turns out that the optimal value of this geometric progression is Q is around 0.17, and this is something that people have investigated. There is a work in the book of Szabo and Babuska where they look into this, and numerically they determine that more or less the optimal geometric projection looks like this. Okay, so let's finish here the lecture. Do you any questions? Do you have any questions regarding this material? No questions. Okay, so we stop here and let's meet in 15 minutes. Yeah.